So good afternoon, everyone, and I'd like to thank the organizers for this opportunity to present my work. So I'm going to talk about pairwise Ising model analysis of human cortical neural recordings, especially in wakefulness and in sleep. So we spend a lot of time every day, every night, sleeping, but we don't really know why. There's still a lot to understand as to what goes on in your brain while you sleep. And so if you look at the scale of the whole brain, so at the electroencephalogram, you can see that there's a clear difference in the brain activity between wakefulness here and deep sleep here, and that the activity during sleep is dominated by this slow, irregular oscillation. So this is at the macroscopic whole brain scale. And what we're interested in is how this works at the microscopic scale, at the scale of single neurons, and how they interact together in neural networks. And fortunately, we have just the right kind of data to investigate this question. The data we work with is recorded with this device, which is called a Utah array, and which is 4 millimeters by side, and it's inserted into the temporal cortex of a human patient. And it's possible with this device to record all the spikes of up to 60 neurons throughout periods of wakefulness and of sleep, and even between these neurons sort out which ones are excitatory and inhibitory. So it's a truly outstanding data set, but it's also extremely complex. So how do we make sense out of all this activity, all these spikes? Well, one way to go about it is to bin these spikes into time bins, and then look at the firing pattern in each bin. So which neuron is active in each bin. And from there, for example, you can look at which neurons tend to spike together a lot, which ones, which pairs are strongly correlated. And what has been found is that the pairwise correlations between neurons tended to decay with the distance between the neurons in all cases except for inhibitory cells during deep sleep. And this synchrony between inhibitory pairs was even very strong across long distances, across different brain regions. So we may wonder from there, what are the dominant neural interactions that we observe? How are excitatory and inhibitory cells involved in them, and how do they differ between sleep and wakefulness? So we looked at the pairwise covariances, but there's many other ways to look at this data set. So maybe we should ask, are pairwise interactions, are pairwise covariances really a good description of what's going on in the system? Are pairwise interactions sufficient to capture the main features of the neuroactivity? So how do we answer this question? We can build a null model for the pairwise covariances, which is the most generic model that only reproduces the firing rate of the neurons and their pairwise covariances by design and nothing else. So that means we need the maximum entropy model for these statistics. So how do we go about building this model now? Well, this is like a Lagrange multiplier problem, where you want to maximize the entropy with constraints that the firing rates as predicted by the model equal those in the data, and the pairwise covariances in the model equal those in the data. So you want to maximize this quantity here with respect to P of sigma, which is the probability of a firing pattern, and minimize it with respect to the Lagrange multipliers B and J. So first, maximizing with respect to P of sigma. We obtain this model that you may recognize as the Ising model in statistical physics, where the parameters are, the B parameters are the neuron's firing threshold, so each neuron's bias towards firing or being silent. And the J parameters are the pairwise functional couplings in between each pairs of neurons. So now that we have the general form of the model, we want to maximize this model's log likelihood with respect to the parameters B and J. So for that, we need the log likelihood gradient. So this regenerates the constraint that we defined before on the firing rates, like how the model relates to the data, and on the what is effectively the pairwise covariances. And to check that this problem is well posed, we can compute the Hessian of the log likelihood. So here's an example for the log likelihood differentiated by BI and BJ. And you can notice that this is the pairwise covariance. And similarly for all other terms of the Hessian, you can express it as the covariance matrix of the model sufficient statistics. So this means the Hessian is a pairwise covariance, is a covariance matrix. So it is symmetric, which means that the problem has a solution and it is unique. So we can solve it. Now, how do we solve this? We can do gradient descent, so we can compute the gradient by running a Monte Carlo simulation with a certain set of parameters, and then just taking the difference between the statistics predicted by the model and the statistics in the data. So this will converge, but it can take very long, and it will take a very long time. So one way to fix this would be using the Newton's method, where we use the inverse Hessian of the log likelihood. But the problem here is that this is extremely computationally expensive, and to do this at every step. So even if you have less iterations, is actually slower than the previous method. But now, remember I said just earlier that the Hessian matrix is the covariance matrix of the sufficient statistics of the model. So suppose the data we have was generated with an Ising model, which is like what we hope, right? Because we want it to be a good model. So then at the solution, you have the pairwise covariances of the statistics of the model, which must be equal to the statistics in the data, because data equals model. That's what we want, right? So so the Hessian matrix is going to be equal to the empirical covariance matrix, and now actually we can take that as an approximation to the Hessian in our algorithm. So it's exactly the same as the Newton's method, but here we replace the Hessian with the empirical covariance matrix. So that means we can compute it once from the data and then start the inference and use this matrix, this empirical covariance matrix, as an approximation for the Hessian. And this approximation will get better and better as the algorithm approaches convergence and as the model comes closer to the data. So we do this, and we find that, and so we just verify that it works and that we get the same pairwise covariances predicted by the model with those that we get in the data. We do that in wakefulness and in sleep data separately. And now we wonder, is this a good model? Now that we managed to fit the model, so we have the model for wakefulness, we have the model for sleep. So is this a good model? And how do we find out? So if it is a good model, it means that it really captures all the main features of neuroactivity. It captures what's going on in the network. So it can reproduce other empirical statistics than the ones that it was specifically designed to reproduce. It can reproduce statistics other than the pairwise covariances which it was fitted on. So this is what we test next. So here we're looking at a statistic that is the probability distribution that a number k of neurons spike at the same time, as in the same time bin. So we can see here that the model and the data are very close for wakefulness. So the model reproduces the data very well, which means pairwise interactions are sufficient. For sleep, conversely, the model doesn't work quite as well, and by looking at it in more detail, you can see that it's for inhibitory cells in blue that it particularly fails. So it means for sleep you need higher order interactions than pairwise, perhaps even population-wide. And this is consistent with the fact that you have this slow, irregular oscillation during sleep, because it's like an oscillation that's population-wide and tends to synchronize neurons across long distances, and especially so for inhibitory neurons, as we said before. So this is consistent with that. And also as a check that we didn't do all this thing with pairwise covariances for nothing, we can see that in the model that would be simpler, that reproduces the firing rates only, and not the pairwise, and has pairwise couplings at 0, so it doesn't reproduce the pairwise covariances. That the model fit is much worse. So it means that the pairwise model is a really good model for wakefulness, in a sense. So to conclude, we found that the neural interactions during wakefulness, they're mostly pairwise. So pairwise covariances are a good description. So the interactions are short range in space, as these pairwise covariants decay with distance. During sleep, you need higher order, maybe population-wide interactions to describe what's going on in the system. So maybe for excitatory neurons, you have more awake-like types of interactions, and inhibitory neurons, because they're so strongly correlated to one another, they may be tuned to the inhibitory population as a whole, and even across long distances. So we've been able, with this approach, to summarize in very simple words what happens in a very complex system with a lot of data. And so we've done this by using null models, so based on models from statistical physics, so the Ising model, and we fitted this model to the data with a data-driven Maxent algorithm, in the sense that we approximated the Hessian matrix with the empirical covariance matrix. And in the future, we'd like to fine-tune our algorithm to more correlated data sets, because these are the ones where it's harder for this model to work, because they're less Ising-like, and also estimating statistics may be harder, and because we use the statistic from the data, then this is one of the challenges that arises. And also extend our methods to other models in the exponential family. So I'd like to thank my collaborators from the CNRS and the Institut de la Vision in Paris, and our very happy looking team. And of course, thank you for your attention. And I'm open to any questions.
Do you know, it's quite surprising that the pairwise model is sufficient, even if it is famous, because you have a sigma p link in the neural network, and we have also synchronous assembly that imply a lot of neurons. So perhaps I'm not sure about the protocol of measurement. So if I can have some indication on the protocol, perhaps I can understand better why the pairwise model is working quite well.
Yes, so your question is about the protocol, like how the data was collected, or? So we have this UTA array, and we can record the electric field that's generated, and we can see different, like we can see spike waveforms in each of these peaks. You can record many spike waveforms, and you can do spike sorting from there by looking at the different shapes of the different forms of the waveforms. And that's also how you can differentiate between excitatory and inhibitory, like regular spiking and fast spiking cells. And really all that we use in this is the spike times.
Because we have time, perhaps I make a comment of this question. Because when you test an easing system, depending on the coefficient, in fact, it could be near just taking in account pair, but it could also take in account much more, because the equilibrium states in easing is not well described by this energy function. If you have sufficiently many data, you can discover something like the true equilibrium, which is very far. For example, if you are near the critical temperature, you don't have analytical computation starting from that. So you have something much more complex than pair interaction, which occurs through this process. Just a comment to justify.
Thank you.
Just one question. How do you separate excitatory from inhibitory cells with those extracellular recordings?
Okay, so one first way is to separate regular spiking and fast spiking cells. So they have a different spike waveform. One of them is basically like faster than the other. So this allows you to make some kind of clustering and see which cells are excitatory and which cells are inhibitory. One other way is to look at the pairwise covariances. So you take one cell, and if it's like negatively correlated with everyone or this kind of thing, then it's an inhibitory cell. And in this data set, what is really remarkable is that like all cells that were determined from their waveform to be fast spiking were inhibitory, and all cells that were determined to be regular spiking are excitatory. So we have a really robust discrimination of the cell types, and we're in the temporal cortex in like layer 2-3, so it's not very deep. So it's a very robust in this case.
In this case, and just for the question of Paul, maybe you can come back because what I think it was referring to the graphic of the probability distributions. Yes, those one. Yeah.
Yep. Okay.
Yeah, I think this is the.
Yes. So it's not. Yeah, it's not like a very. It's probably not a very general thing. There's many data sets where the model might work, and then because you have very strong synchrony in the population, for example, you really need interactions that are higher order. But this is something you see in the temporal cortex during wakefulness. So it's like the activity is fairly sparse there. So you wouldn't expect like any like big group population bursting or anything like that. But
yeah, but here, for instance, K is one state, is one possible state of the whole network.
So K is so it's like when you have K neurons that spike at the same time. you can have any of them. For example, if K is 2, you can have any 2 neurons in your network that are spiking in that time bin.
Yeah, sorry.
Another question? First, I have one question. Okay. Because during sleep or awake when something happens, okay, you have necessarily non-stationary phenomena. Okay? That's it's for example in sleep to explain spindle or ripples. Okay? It's not possible with a stationary distribution. Okay? So you are out of equilibrium. Okay? So
Yes,
that's an interaction between a model of equilibrium, okay, and the perturbating phenomena which came from out of equilibrium activity. Okay. Even if ripples are localized, okay, so they synchronize with other areas than temporal. Okay. But still, there are events which appear in time and which are not stationary. Okay. So how it's possible to incorporate non-equilibrium phenomena in this kind of model?
And so thank you for your question. It's a very interesting question. Since if we're doing models from statistical physics, somehow we need to look at the whole statistics. Then so there's several ways to answer this. So just to come back on your point about sharp wave ripples and spindles, it's actually been found that these the phase of this oscillation, this oscillation is synchronized in the cortex with the spindles in the hippocampus. So already reproducing this kind of activity is non-stationary in the way you were saying. So we had a model that is similar to the easing model. Just looking to this model, but instead of considering the correlations between each cell and each other cell and the couplings between each cell and each other cell, we can take into account the coupling between each cell and the whole population. It's similar to the models of no, not really. Well, mean field is more like you have a tuning function, but it's kind of a similar idea. It's yeah, so Harris models and Okun 2015 paper. And so with this model, we were able to reproduce the dynamics during sleep better, even though it's got this very slow, irregular oscillation. Because well, the population activity is something that varies throughout time, and we're considering the couplings between the cell and the population. Also about time dynamics more generally, it's true that these kinds of models do not take into account time at all. So you just consider that it's an equilibrium state, and you don't consider what happened in the time bin before, the time bin after. And that's also something that people are working on, extending this model to take into account time. And one possible way is to do a kind of Markov easing model where you have couplings between a neuron and itself in the previous time bin, or another neuron in the previous time bin. And there's a paper about this where there's at least Olivier Maire and Alain Destex who are collaborators in this paper. It's an older paper. I think it's 2009 on top of my head.
Thank you very much. So there is no more question. Thank you.